For any algebra, we define an algebra by this notation that contain A and have a unit, so that this is a unital algebra and A can be embedded in this algebra. Okay, now okay, the intersection of all maximal ideal denoted by the radical of A algebra is called radical if the radical space of A equal to A, and the algebra A is semi-simple if the radical of A equal to 0. Okay, so that we have this definition. Let A be an algebra and, for example, we can consider M equal to the set of all maximal ideal subsets of this unital algebra such that I is a maximal ideal. Okay, maximal ideal in this space. Then we define the radical of A equal to the intercept of all M such that M belong to this maximal ideal space. Okay, this is the set of all maximal ideal in this unital algebra. So this is the definition of radical space of A, and two okay, two This is this definition. A is called radical. Radical whenever rad A equal to whole of A, okay, and the algebra A is called semi-simple. A is called semi-simple. Simple whenever the radical space equal to only 0, okay, and this is definition 3. It is easy to check that in the unital case we have this equality. So we have this proposition let A be a unital algebra then we have this equality rather A equal to the set of all A in A such that for each B in A, EA minus BA be invertible element in A. Okay. Dear students, do you have my voice? Okay. Dear students, we write this definition. Let A be an algebra and M equal to the set of all maximal ideal in this algebra. Then the radical of A defined by this intersection of all elements in this maximal ideal space. N is called radical whenever this set equal to the whole of A, and A is called semi-simple whenever the radical of A equal to 0 only. Now we have this proposition that this is applicable proposition, the radical of A equal to the set of all A such that for each B, EA minus BA be an invertible element in A. Okay. And for its proof, we can see that if A belongs to this set, let EA minus BA is invertible for all B in or algebra. Let M be a much considered unital algebra. Okay, we prove that we will prove that, or we want we will prove that A must be belong to this M. Because by contrast, if we consider or if we assume that A not belong to N, since we see that N plus A is an ideal in A containing M. It is very trivial that this is an ideal because for any x, for example, in A, if we multiple x in each side of this set, the result is a set in the set again. Okay, for each x in A and for each m in N, A1 and A2 in A, we see that x n plus x A1 A2 is an element of this ideal. It's very trivial because this is equal to xm. xm is an element of x. Okay, let me write this is equal to xm plus okay, plus x a1 a2, and this is an element of m plus a. It is very trivial because this is an element of m, because m is an ideal, and this is an element of a. Okay, and similarly, if we consider this element multiplied by x, this is in this ideal again. Okay, and similarly, for any x in A and y in m plus a, yx is an element of m a. So m plus a is an ideal. Okay, also for any j, for example, in M, we see that j equal to j plus zero a 0, and this is an element of m plus a. So m is a subset of m plus a. Okay, so this is an ideal and this is containing M. Okay, but M is an maximal ideal in A, so that we don't have any proper ideal after M. So we have one of these two cases, M equal to M plus A, or M plus A equal to whole of A. We must have one of these cases. If we have this case, the first case, M equal to M plus this multiplication, then for any J in M, J plus E of A E of A is an element of M plus this ideal, okay? Because EA is an element of A. So that this is an element of this. But we assume that this is equal to M. So there exists, or there is a J1, for example, in M such that J plus EA equal to G1, and this is equal to A, okay? So J plus A equal to G1, consequently A equal to G1 minus J, and this is an element of M. And this is a contradiction because we assume that A is not an element of M, okay? And this is a contradiction. Okay, so this case is not hold. So the equality m equal to this ideal is not hold, therefore we must have this case m plus is ideal must be equal to whole of a. So there exists one element such as a1, for example, in A such that and also there exists a1 in A and J in M such that J plus A1 AA, for example, equal to E of A, because we know that this is an element of this set and this set equal to A, and we have EA in this algebra. So we can consider A1 and A2, okay? And this shows that EA minus A1 A2 is an element of J. But this is an invertible element because we assume that the radical of A equal to because we assume that this is an invertible okay. We want this be A, okay, and so we can consider by this form. And we write this, okay, A. This is an element of J. And also this is invertible by our assumption. Okay, so J must be the whole of A, and this is the contradiction. Please note that please note that so this J must be right M instead of this, because we consider the maximal ideal M. Okay, please note that if J be an ideal and J is the invertible, then J must be equal to whole of A, because for any x in A, for example, we can write x equal to x J inverse multiplied by J, okay, or we can write x multiplied by E, and E equal to the inverse of J multiplied by J. And this is an element of J, because this is an element in A and this is an element of J, okay. For any x in A, x must belong to J, so that A is a subset of J, and so that A must be equal to J. And this is a note, very simple note, that if we have any ideal that have an invertible element, this ideal must be equal to whole of A. Okay, so we have this assumption that we have a contradiction, so that this assumption is false. If we have A not belong to any maximal ideal, we have a contradiction. So this contradiction shows that for any maximal ideal in A such as M, we have A must be belong to M. So A must be belong to the set of all maximal ideal in A. M is a maximal ideal, okay, and this is our radical space. Okay, conversely, let A be true in this intersection B in the intersection of all maximal ideals in A. If there is an element such as B in A such that EA minus BA is not invertible, we have one is an element of sigma BA, okay, because this is not invertible. So is not 0 only. Let lambda in sigma BA satisfy this equality, the absolute value of lambda equal to a spectral of this set, and we know that this is a positive. So lambda EA minus BA is not invertible by this, okay, is not invertible. Hence A multiplied by this and multiplied by A is a proper left ideal. And we know that this is lambda multiplied by EA, okay, it is very trivial. Because this must be proper, because if this equal to then there exist two elements in A such that A1 lambda EA minus BA multiplied by A2 equal to EA, and this shows this element is invertible and also this element is invertible. This element is invertible. And this is a contradiction, okay? So that this is a proper left ideal, and we know that any proper left ideal is contained in the maximal ideal. So there exists a maximal ideal such as M with this property. that this ideal be is a subset of this n. So and this is again lambda EA is an element of n and also by assumption this A must be belong to M because we consider A in the intersection of all maximal ideal, so that A must be belong to any maximal ideal such as M. Okay, and this shows that Bm must be belong to M because M is an ideal equal to lambda EA minus BA plus BA must be belong to M, and this is a contradiction because this is invertible element. Or from this we can see that EA must be belong to M, and this is a contradiction because M must be equal to whole of A. So we have a very nice equality. The radical of A equal to the set of all A with this property for each B in A, EA minus BA be invertible. Dear students, do you have my... Okay, I don't know, you follow your my proof, and do you understand this or not? Let me write and have a question for you. هل تتابع المحتوى أم هل تفهم البراهين؟ Dear students. Okay, very good. Very okay. So we prove this equality and also we have some other facts such as this. The radical of A is an ideal. Okay? The radical of A is an ideal. Let me write this. Let A be a unital algebra, then this is an ideal. In A, okay? And its proof is easy because if x belong to A and y belong to the radical of A, then by the previous proposition, we have for each B in A, EA minus BY is invertible, okay? Is an invertible. By this fact, EA minus BY, because we consider Y in the radical of A. So that we can by this method or simpler, okay? Let me write this. This is very simple. Then by the definition, okay, for any maximal ideal of A such as M, we have Y is an element of M. So we have so since M ideal, we have xy must be belong to M. Consequently, xy must be belong to the intersection of all maximal left ideal. M is the maximal left ideal. Left ideal, okay, and this shows that xy must belong to the radical of A, okay. So we prove that for each x in A and for each y in the radical of A, we have xy in the radical of A. So the radical of A is an ideal and let me check this or definition. Dear students, maximal left ideal, it is at maximal left ideal, okay. So in this proof we can, dear students, for left ideal in this proof we can consider this only, okay, because this is a left ideal. Let me correct this, and left ideal, because we want left ideal only, left ideal, and for this set element have this form, A1 only enough, okay. It is better please correct this, and this is A1 multiplied by A and this is okay. Okay, this is our left ideal and it is enough. So we don't have this because we want a left ideal, not ideal. Okay, and we can remove this line. Okay, okay, and okay. But M is a maximal ideal, is maximal left ideal. Okay, maximal left ideal. So this is equal to M or this is equal to A. If we have this, and this is in M, so there is J1 such that this is equal to J1, and so this must belong to M. This is the contradiction, so the equality is not whole, this equality, therefore this equality must be whole. Okay, so there exists A in A and J in M such that, okay, this is okay, let me write, this is equal to EA, the identity element of A, so EA minus A1A, A1A, okay, must be belong to M, and also this is an invertible by our assumption. So M must be equal to A. Okay. Other proof is true. Maximal left ideal. Maximal left ideal. Left ideal. Okay. And in this, for the converse also we don't need to this side because we want only left ideal, only left ideal, and our proof be more simple. Okay, this is equal to EA so that this must be invertible. and also we can omit this A and this proof is complete. Okay. I'm very sorry for this correction, and by this correction our proof is complete and more clear. Okay. Dear students, do you have any questions? For your attention, thank you very much.